To move through the digital world, every entity must first be assigned a definitive identity. In a network, data requires a precise origin and destination. For decades, that identity has been defined by IPv4. It uses a 32-bit addressing scheme, which means it can generate about 4.3 billion unique IP addresses. When the internet was designed, that seemed like plenty. Today, with billions of smartphones, computers, and smart devices continuously connecting, we have effectively run out of room. This table contrasts IPv4 and the upgraded standard IPv6. Looking at the address availability row, IPv4 hits a hard ceiling at 4.3 billion. IPv6 expands this space to 340 undecillion unique addresses, a practically infinite runway for future devices. The exact protocol version doesn't change the underlying rule. Without an IP address, data is invisible. It is trapped. Digital identity is the absolute prerequisite for digital movement. This table identifies private IP address ranges operating as localized identities, allowing devices to communicate strictly within a contained network. Notice the text above. These are not routed on the internet. They explicitly prevent communication with the outside world. To breach that local perimeter, data must pass through a checkpoint called Network Address Translation, or NAT. NAT acts as a proxy, taking the internal traffic from dozens of private devices and masking them all behind a single outward-facing public IP address. These identities can be assigned in two ways. A network administrator can manually assign a static IP, guaranteeing the exact same address every time. Alternatively, a DHCP server can dynamically allocate a temporary address from a predetermined pool, rotating IPs as devices join and leave. Regardless of assignment, passing through NAT to acquire a public identity is the crucial first hurdle. Without it, local data can never escape its containment. Once data is cleared to leave the local network, sending it as a single massive file is highly inefficient. Instead, the data shatters. Through a process called packet switching, the original file is segmented into small, uniform packets. Each packet is wrapped in a header, a tiny block of metadata containing the source IP, the destination IP, and a sequence number. These packets do not travel in a straight single-file line. They are transmitted independently. Depending on network congestion, one packet might travel through a cable under the Atlantic, while the next takes a completely different route, before they all use their sequence numbers to reassemble perfectly at the destination. This fragmentation is a survival mechanism. By breaking the transmission apart, the network ensures that a single severed cable or jammed connection cannot destroy the file. But those independent packets eventually have to travel across real physical hardware. They move out of the software layer and into the cables and frequencies that make up the physical grid. This table compares the physical media carrying those packets. Looking at the first column, fiber-optic cables transmit data using pulses of light. This yields extremely high bandwidth and total immunity to electromagnetic interference, though it requires specialized tools and heavy investment to install. By contrast, twisted pair copper cables transmit data via pulses of electricity. They are highly cost-effective and easy to install for local networks, but they suffer from signal degradation over long distances and are vulnerable to electrical interference. Wireless networks solve the physical tethering problem entirely by broadcasting electromagnetic waves. However, as the security row points out, broadcasting data into the open air makes the transmission highly susceptible to physical obstructions and unauthorized interception. Every step a packet takes involves a physical medium, and every medium represents a strict calculation balancing speed, cost, and the risk of capture. As millions of packets rush through these copper wires and glass fibers, they hit hundreds of physical intersections. At every junction, a hardware device must read the header and instantly decide where that packet goes next. Inside a local area network, that job falls to a switch. Switches read hardware MAC addresses to direct data to specific devices on the same internal network, effectively managing the local traffic flow. But to cross the global internet, packets rely on routers. Routers operate at a higher level, reading the destination IP address of each packet to navigate the massive interconnected webs outside the local facility. Think of switches as the managers keeping the internal facility running, while routers are the navigators actively charting a course through the external maze. To chart that course, every router references an internal map called a routing table. How that table is built determines how resilient the network actually is. This table compares static and dynamic routing. In static routing, a human explicitly programs paths into the table. It is secure, but look at the convergence row. The routes are fixed. If a link breaks, the router cannot adjust. Packets are dropped. This diagram visualizes dynamic routing. Routers communicate using protocols to exchange connection and topology data, continuously calculating the fastest path. If a node fails, marked by the red X, the network experiences convergence. Routers instantly recalculate tables to redirect traffic around the failure. The moment a path is blocked, the swarm of data adjusts its route in real time, bypassing the damage without a single human intervention. The internet operates as an autonomous, self-optimizing organism. By fragmenting data and empowering hardware to dynamically route around failure, the network ensures that once a transmission is free, it will always find its destination.